Complex can be complicated. Big data is often multi-scale. There may be some randomness, but that's not the real issue. It's the complexity, and so we need models that are also complex. So where does data come from? So if we have a well-defined process or system, there's also going to be some noise. And data is observations of a process or system plus that noise. We often call the observation due solely to the process the signal. And so data we can think of as signal plus noise. So data is signal plus noise, and we say it's sampled from the process or system. Mathematically, we say each lowercase xi is an instance of a variable uppercase x, or a statistics we call it a trial. For example, let x be the height of a human chosen at random. A single trial might be something like little x equals 6 feet, and we would say that's an instance of the variable capital X. So what exactly is a variable? Well, a variable is associated with a set. Any value in the set can be an instance of the variable. Any instance of the variable has to be in the set. For example, suppose we look at the set of all possible clock outcomes, where variable capital X is the valid clock time, and all instances of clock times are valid clock times. Notice that we have some notation here. A variable is in uppercase italics, and if you have the lowercase italics, then we're thinking about instances from the set. A variable is often described by how it takes on value. Regular variables take on values predictably with respect to the ordering of the set. Clock outcomes is a regular variable. Notice that if you have a regular variable and the x is lowercase x is the index or the instance is the regular variable, then they're going to be the same. So often we'll use capital X and lowercase x interchangeably when we have regular variables. Very common in calculus, for instance. A variable, however, could take on values at random. And it could also be neither random nor predictable. What? That may sound strange. So unpredictable but not random. Not random is the same as deterministic. And unpredictable refers to human limitations. So for instance, digits of irrational numbers do not occur at random. There are algorithms for generating digits of pi, and yet if you tell me what the first n digits of pi are, I can't predict what the n plus first digit of pi is going to be. The motion of a molecule in some kind of a wiggling protein computer simulation, it may look random, but in fact it's completely deterministic. So there is a deterministic, which means non-random, pattern to how a chaotic variable takes on its values, but we may not be able to understand that pattern. But we may not need a complete understanding to make predictions. And we shouldn't focus on individual variables. We're modeling a process. Our goal is to understand the process. For example, we can sample more than one set of data. And having done so, we have two data sets, different sizes of independent trials of a variable X. True results are independent of both data sets. And our goal is to explain the variables, or equivalently the process, independent of the trials and also of the noise. But usually there are many variables, capital X1 to capital Xn. So when we think of data, we think of M observations of N variables. And then our goal is to learn from one set of data and to predict outcomes from another set of data. We can do this using a model of the process. So what is a model? It's a function of our variables. It constructs a representation of the data that we're going to be using as our training set and makes predictions about the data that we're going to use as our test set based on that representation. So we're going to have a training data set and a testing data set. So where does modern data come from? Well, it's sampled from complex systems. Complex systems are real-world systems that have a mixture of regular and chaotic variables. The variables are not linearly related, so the sum of the parts is not the same as the whole. Complicated underlying non-random structures. For example, the Lorenz attractor was discovered in the winter of 1961 by meteorologist Edward Lorenz. He saw something new while he was doing a numerical simulation of atmospheric dynamics. And he distilled what he was working with down to 3 equations that still had this new phenomenon that he was observing. He figured out what parameters to use to produce this new phenomenon and produce what's known now as a strange attractor that resembled a butterfly. So clearly, if you look at this strange attractor, it has a complicated underlying structure. And the underlying structure is what we call a topology. Now, I'm not thinking of the field of topology, but topology in its actual meaning as the way in which constituent parts are interrelated or arranged. In other words, the underlying structure. Values of the individual x, y, and z coordinates are unpredictable. For example, if you had a time series for the x coordinate as a function of time, then it's going to look like it jumps from below 0 to above 0 at random. But that's not random. So even though the motion may look like it's random and unpredictable, it is unpredictable, but it's not random. In fact, we could create from just the single x coordinate a topologically equivalent structure. We choose a sufficiently large tau, which is a lag, and then in 3-dimensional space, we can create a structure that is topologically equivalent, same shape and structure, slightly deformed perhaps, to the Lorenz attractor. So there's the reconstruction, and it's topologically equivalent to the original. So modern data is sampled from complex systems, but we still have noise. So in the real world, data collection is noisy. Here's our nice x coordinate from the Lorenz attractor. But this is what we get from the real world, a noisy version. But if the noise is not too loud, then once again, we can get a topologically equivalent structure. Maybe one that's not as pretty, but still equivalent. So everything we've done so far is via algorithms. So I want you to notice simulations are with algorithms. Equations are algebraic expressions of a process, but we can't solve these equations. They're numerically estimated. That numerical procedure is an algorithm. So we've been doing everything so far in terms of algorithms, and we need to think of functions as algorithms. And we'll be looking at a lot of functions that are algorithms that you can't define with equations. For example, let's build a multi-scale function model. And what we're going to do is we're going to have a pattern, a template, and in each iteration of our algorithm, we're going to replace a straight line by this tent structure where we're keeping the edges of our template vertical. So we'll take this line, we'll replace it by this pink union of 2 lines. We're also going to maintain symmetry about the point x equals 1/2, and that's just so it looks good. So here we have our original structure. There's our template. We're going to take the brown lines and and replace them with the green and the blue respectively. And then we're going to do it again. So there's our template. Put it all over the place, keeping those things vertical. And we get another iteration, and we can just keep doing this ad infinitum. And in the limit, we actually get a structure, and it's a function. It must be a function because we kept those line segments at the end of our template vertical. So this function is self-similar. If you zoom into any level, you're going to see the parallelogram template that we used at that level. It's continuous by construction, but you can't zoom into a single scale straight line. In other words, this function is differentiable nowhere. But we can use a function like this just like we use elementary functions, even though they're defined by algorithms. And such functions tend to be more real world as models. For example, branching structures are very common. So we have a trunk segment, and then the algorithm says we branch to the next iteration, and then each of those iterations branches again, where each is only 75% the diameter of the parent. So what happens? The diameter is changing. The surface area and the volume is also going to change. And notice what happens to the surface area is we'll have the surface area for the first, it's a cylinder, and then also for the second and the third iterations. And if we keep going, what we end up with is the surface area goes to infinity, but the volume does not. I can put this broccoli-looking structure in a box. This is what's known in the life sciences as the fractal advantage. A fractal structure can have finite volume and infinite surface area. And higher order organisms use the fractal advantage. This set of human lungs branches more than 20 times, so that we have essentially infinite surface area in our lungs with which to exchange oxygen and carbon dioxide from our blood with the atmosphere. Now, fractals are everywhere, according to Michael Barnsley. Everything you're looking at here is known to be a fractal, including this image where nothing here is real. Every single thing you see in this image is a fractal. That is, these underlying topologies of big data are complex and multi-scale representations of the real world. But we only need topology in its most basic form: limits, derivatives, integrals, and series. So in summary, we're going to sample variables to produce data, and often one of these variables is unpredictable. And as typical in practice, we'll use the term random variable to refer to any variable that's unpredictable, including chaotic variables. This is something that we do, and we'll do the same. There's also going to be some noise. A complex system or multi-scale process has a complicated underlying structure. The world itself has a complicated topological underlying structure. We're going to look at questions about emergence, which are about the data as a whole rather than an individual variable. And we're going to focus in particular on things which can be answered using our now well-established background in calculus.